Let's talk a bit more about transformation of functions. When we talk about transformation of functions, we mean lots of different things. We could be moving the graph left or right, so we could have a horizontal shift. That's one type of transformation. So horizontal shift means the graph is picking up and moving left or right. We could have a vertical shift, moving the graph up or down. We could have a reflection, so the graph reflects. And then the graph could actually change in its like narrowness or wideness. And typically we would refer to that as stretching or compressing. And technically there could be vertical or horizontal. Let's just write stretching, compressing. So this can be a lot to digest, especially if multiple transformations are occurring within the same function. So attached to today's topic, we have a little handout called toolkit functions. And what that gives us is some base graphs for common functions. And then from those base graphs, it's actually kind of neat to talk about using our knowledge of transformations to create graphs or equations. So we'll just explore a little bit. I think I'm going to pick on our absolute value graph for our examples today. We've talked about this a bit previously, but it probably could still use some discussion. So I'm just reminding us of what that graph looks like. It's that nice V shape. We built it from scratch before. We can tell its domain and range. We know where it's increasing and decreasing. And using that base graph, let's see if we can graph a transformed absolute value graph. So don't worry too much about this part. I was just kind of jogging our memory with the basic shape. And let's try an example. So what I'd like to do is ask us to use the base graph of f of x equals the absolute value of x to graph a transformation. And I'll call the transformation g of x just to give it a different name than f of x. And let's say in this transformation we have the absolute value of x, and then let's say it's minus 2 plus 3. So we want to explore together how can we use simply the base graph to create the graph of the transformation. Because if all we did was walk on the scene and say, hey, plot this, that could feel a little harder. We could always build a table of values though. But let's see if we can pick off just our knowledge of the base graph and our understanding so far of what causes horizontal and vertical shifting. All right, so let's get a little coordinate plane going. And let's see, I think I can even give us that. That might help out even more. I'll just make it regular graph paper so I can move my origin around a little bit. Okay, so on our coordinate plane, I am going to take a brief moment to redraw the base graph of the absolute value function. You may feel like we've done this enough times, but still just a good idea. So the absolute value function, like we just saw, right, passes through 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. So I'm just going to plot a couple points to get that nice V shape. So 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. So I'm plotting in blue here the base graph. Now we get to talk about how is the new graph g of x different from the base graph? What transformations have occurred? And earlier we talked a little bit about horizontal and vertical shifting, reflecting, stretching, compressing. And it turns out that whenever you have a change within the function, so something like, I'll try to write a very general feeling, x, I'm going to say plus h, and then I'm going to say plus k. We've talked a little bit about the fact that h is tied to that horizontal shift, so I'm just color coding here. So anything happening within the input is going to adjust the left-right motion. The vertical shift is just tagged on to the end. So any value being added or subtracted at the end of the function could indicate that up or down shift. It turned out that reflection, stretching, compressing, these are all tied to a coefficient out front of the function. I've been using a to hold the place of that coefficient, so those values would be tied to the a value out front. So with that brief recap, I hope it seems logical then to say that this -2 within the absolute values, this is shifting in the horizontal direction. So this shifts the graph 2 units. And which direction? This is where we have to be a little careful. Horizontal shifting, I always feel, is a bit counterintuitive because a negative actually shifts the graph to the right. So this is going to shift the graph 2 units to the right. And then the +3, right, we were talking about the vertical shifting. That's going to be a vertical shift in the upward direction. So this +3 here shifts the graph up 3 units. If it were a -3, then it would have shifted the graph down. Awesome. So what's neat about this is I'm trying to create a graph that accomplishes these two things, and it's not as hard as it sounds if we take it point by point. Here's what I mean by that. You can see very clearly that the origin 0, 0 is a point on the base graph. So what I'm going to do is take that origin point, shift it right by 2 units, so 2 to the right, shift it up by 3 units, 1, 2, 3, and plop down a new point. So I'm doing really kind of a point by point transformation. So the absolute value has kind of a very clear point at the V, right? That's a good characteristic to pick up on. And all I just did was move that V. Now, if I want from there, I can literally just start moving, right, up by 1, over by 1, because I know that's the behavior of the base graph, and there's no coefficient out front that's adjusting the slope. But I can even be a little bit more thorough about my approach and pick up on another point. How about this point right here? This point right here is -1, 1. And I can do the same motion I did to the point 0, 0. I can take that point, move it 2 units to the right, move it 3 units up, and there is the new location for the g function, because that point has now been moved right and up. Let's do one more that way. I think I can find one more color here. So let's pick on this point from the original graph. It's getting a little crowded, but this original point was 1, 1. I'm going to move that point 2 units to the right, and then I'm going to move it up 3 units, and I'll put my point down. And now I have 3 new points for the transformation graph, and that's probably enough to connect them and say, there it is. So let's go ahead and do that. I know with my scribbles it looks a little busy here, but we'll see the end result very quickly. So in purple, we are showing the new graph. The graph of the absolute value function picked up, moved to the right 2 units, and shifted up by 3 units. When you think about moving an entire graph, it can feel overwhelming, but if you just take it a couple points at a time, it's not too bad. So the last thing I'd like to do with you all is work this kind of in reverse, meaning I have just 2 graphs to look at, and I want to talk through, given the graphs, can we determine the equation of the graphs? So sometimes working backwards in that way is a bit of a stretch, but what I will give us is I'm always going to graph the base graph in blue, and we're working with a base graph of the absolute value. So for this first example, my goal for us is actually just to determine what is the equation of this red line, and I'll call it g of x. So I want to find equation for g of x. And all I got to use is my knowledge of transformations. So many ways you can do this. Turns out this graph maybe looks a little similar to what we just did. Sorry about that. But a good starting point is just to compare an easy to identify characteristic, which on the absolute value graph is the base of the V, right? Where the line shifts from decreasing to increasing. So if I asked you just to determine what happened from that first yellow point to the second one, I think we would have a pretty easy time establishing that it seems to have moved right by 2 units and then up by 3 units. Identifying those two changes is actually enough to build the equation of the red line, because we know if the graph is shifting to the right, that means I've got to do some sort of change within the absolute value. A right shift is actually indicated by a negative, and it was 2 units, so I have a -2. And then the graph shifted up by 3. So vertical shifting, a positive indicates up, and we tag that on to the end of the function. So transformations really can be that easy. The other thing we should check though, because the next example will blow this theory just a tad, is notice that on the base graph, we just go up 1 over 1, up 1 over 1 to get to the points on either side. So just make sure real quick that that same slope is seen in the transformed graph here, and it is. So turns out there were only 2 transformations. There was the shift to the right, and there was the vertical shift, the shift up. So this would be the equation. Let's try one more of those and then we'll call it good for now. This one will be just a tad bit harder. I think at first glance you can notice that the slope of the transform graph is different than the slope of the base graph. So that's something that we did not have in the last example. So the blue graph again is our base graph for the absolute value function. We're trying to figure out the equation of the green graph, which I'll call G again. So our goal is to find an equation, just like in the homework, for G of X. And we have to ask ourselves, okay, well, what changes happened from F to G? Picking up on that key kind of V point here, right there, it looks like all it did in terms of actually picking up and moving was it looks like it shifted left by 2. So I'm just going to take a minute and write these changes down. Shifted left by 2. So I think we know how to handle a left shift. But then if I use my little test of going up and over from the V, the base graph again is up 1 over 1. But on this new graph, you can see I'm going to get to the next clear point, I'm going up 2 over 1, up 2 over 1. So that means the graph is narrower, right, or steeper, I could say, than the blue base graph. So that's a new challenge. So graph is narrower. And really, I think you may have heard me give you that coefficient because it's a calculation of slope, right? So out front of the base graph, you can understand the absolute value of x technically has a coefficient of 1 or 1 over 1, and that's giving us the slope, right? Now, for our transform graph, I mentioned a moment ago, I went up by 2 and over by 1. So that sounds to me like it has a slope of 2, right? It's either positive 2 on the right side or negative 2 on the left side. So the coefficient that we get to use to write the equation for g of x will be g of x equals, we stick that coefficient of 2 out front to adjust its slope, and then we have the absolute value of x within the absolute value bars. To get that shift left by 2, we need to add or subtract 2. If you're going left, remember left shifting is actually indicated by the addition of a value. Whew, so that one's a little harder, but again, hopefully these ideas are making a little bit more sense. Transformations are really neat. And if these ideas are seeming a little bit more clear, you are in good shape not only for the rest of this class, but actually for future classes as well. Transformations continue to occur.